Hello. Good evening, all. I'm Saurabh and I welcome all of you to this session for the NPTEL course IC Engines and Gas Turbines. So, this is session 4, and in this session, we will be discussing some problems related to fuel injection systems. Okay. Let's start. Question number 1. It says that pintle type nozzles are advantageous because there are four options. Option A, they operate at higher injection pressures. Their plunger mechanism reduces clogging. Option C, suitable for open combustion chambers. Option D, they have multiple orifices. So, you have studied different types of nozzle, and pinted type nozzle is one type of nozzle, right? So there are certain advantages and certain disadvantages of these nozzles. So pintle type of nozzle has what advantages? So this has been discussed in the lecture, so I think you can easily answer this question, that their plunger mechanism reduces the clogging, right? So you know what is clogging? So clogging is basically, that nozzles have certain holes. Okay, from those holes the fuel comes out, but sometimes the carbon particles or deposition takes place at those holes. So those hole gets blocked, right? So from time to time those holes need to be cleaned. Okay, so this blocking is basically what we call clogging, right? But in pintle type of nozzle, there is plunger and that is moving. So because of moving plunger, uh, this clogging, the probability of clogging is reduced, right? So chances of clog formation is very less or negligible. So this is one of the advantage of pintle type of nozzle. Okay, so correct option is the option B, right? But if you consider other options as well, for example, option A, that they operate at high injection pressures. So yes, they can operate at high injection pressures, but that is not the advantage of this pintle type of nozzle, because other nozzles, so any standard nozzle can also work at higher injection pressure. Okay, so this is not the uniqueness of pintle type of nozzle. Option C, that they are suitable for open combustion chambers. So is this correct? No, this is not correct, because pintle type of nozzles are okay. So if you see option C, uh, that pintle type of nozzles are suitable for open combustion chambers. So is this correct? So can you please answer that? Correct option is option C, that pintle type of nozzles, their plunger mechanism reduces the clogging. But if you consider other options, for example, option C, that they are suitable for open combustion chambers. So is this correct? This is not correct, right? Because pintle type of nozzles, they are suitable for turbulent chambers, right? So they are not suitable for open chambers. Okay, so they are suitable for turbulent type of combustion chambers. Okay, and option D says that they have multiple orifices. So this is also not correct, right? So if you see the diagram, so from diagram you can see that the difference between geometry of a standard nozzle and a pintle type of nozzle. So in a standard type of nozzle, you can see that there is a needle, right? Needle. And in pintle type nozzle also there is a needle. Okay, but you can see that in standard type of nozzle there is a sac volume. Okay, there is a sac volume. So when the needle moves up, so what will happen? The fuel will come inside the this sac volume, and from the hole it will come outside, right? But in pintle type of nozzle, you can see that there is no sac volume, right? But the needle itself is going through this opening, okay, through this hole, right? So when this needle will move up, the fuel will come outside the hole, okay? So in standard nozzle, there is sac volume, and in pintle nozzle, there is no sac volume, okay? And the standard nozzle, in standard nozzle there can be many holes. Okay, in this picture there is only one hole it is shown, but you can have many holes. For example, one can be like this, another can be like this, another can be like this. Okay, so there can be many holes, multi-hole. Okay, but in pintle hole there is one simple single hole, right? So these are some differences between a standard nozzle and a pintle type of nozzle. Okay, but the pintle type of nozzles are suitable for turbulent chambers, right? Right? Because in turbulent type of chambers, there is high swirl, and because of high swirl, this fuel can get easily mixed with the air. Okay. But the advantage is that if there is some carbon deposition, then due to the motion or the movement of this needle or the plunger, those depositions will be removed. So there will be less requirement for less less require for maintenance. Okay. So there are many other type of nozzles as well that you can refer to any book, or just google the google different type of nozzles, that you can see the differences. Okay, so now we'll move to question number 2, that self ignition temperature of petrol is higher or lower as compared to diesel. So you know what is self ignition temperature? Self ignition temperature is the temperature at which the fuel will auto ignite. Okay, so what I mean by auto ignition is that if you know the difference between diesel engine and petrol engine, then I think it is quite obvious that in petrol engines, for the ignition we are using a spark plug, right? But in diesel engine we are not using any spark plug. Okay, then how the ignition is taking place in diesel engine? It is taking place because the diesel is injected in a very high temperature ambient. Okay, because you know that in diesel engine only air comes in, and that air gets compressed in the compression stroke, and when it is compressed, the uh, temperature and pressure becomes very high. And when in that high temperature air, when the diesel is injected, the diesel get auto ignited, right? So the temperature, the minimum temperature at which the fuel can get auto ignited, that is called self ignition temperature. So we have to tell that self ignition temperature of the petrol is higher or lower than diesel. So four options: lower, higher, or same, or none of the above. I hope you can easily answer this question.
Higher.
Yes, auto ignition temperature of petrol is higher than diesel. Okay. So there is a number related to auto ignition temperature. So you know what that number is? Basically, that number tells that how easily a fuel can be auto ignited. So you know what that number is? You know octane number? And one more number is there, that is called C10 number. You know C10 number? Have you heard about C10 number?
No, sir.
Okay, you know octane number? What is octane number? So octane number is something related to the ability of a fuel to resist the auto ignition, or the knocking. Okay, so the octane number is very important for SI engine fuels, right? So for petrol, we want higher octane number. Okay, so if a fuel is having higher octane number, so that means that the chances of knocking will be less, right? If the octane number is low, then there will be higher chances of knocking, right?
Yes.
So knocking. First of all, the important thing is that you should know knocking. You know what is knocking? If you don't know knocking, then I will briefly explain what is knocking. Okay. So in an SI engine and an spark plug engine, you know that the fuel air mixture comes in, right? What comes in? Fuel air mixture, right? Air plus fuel. This mixture comes in the cylinder. Okay. Then it get compressed, right? It get compressed. Then near the TDC, the spark plug ignites this fuel, right? Spark plug ignites this fuel. So when the spark plug action takes place, then there is development of some fuel kernel. Okay, development of flame kernel. Then that flame travels, right? Why it travels? Because in this cylinder, what you have? You have air fuel mixture, correct? You have air fuel mixture. So this flame, this flame front travels, right? This flame front travels, and here you have, let us say, piston. Okay, you have piston. So behind this flame front, this part has been burnt, right? This part has been burnt gases. But in this portion, these are unburnt gases, right? Unburnt gases, correct? But since combustion is continuously, progressing, and this flame front is, traveling, right? So what will happen in this region? In this region, temperature and pressure is also increasing, right? Temperature and pressure is increasing in the whole, combustion chamber. But in this region, there is you know, unburnt air fuel mixture, right? But sometimes what will happen? The temperature and pressure will increase to such a limit that there can be uncontrolled auto ignition. Okay, auto ignition can take place here and there. Some auto ignition will be here, some auto ignition will be here, right? So there will be combustion at some random places. Okay, so that combustion is, uncontrolled combustion, and you will get some knocking type of noise, and that type of combustion is called, knocking. Okay, and knocking is not very good. It is bad, right? It will produce a lot of vibration, a lot of noise, and it can also destroy your, engine. Okay, so we don't want knocking, correct? But the important thing to note here is that knocking is taking place because of auto ignition, right? Auto ignition of what? Auto ignition of this unburnt mixture, right? Auto ignition of unburnt mixture. So you don't want auto ignition of, petrol. You don't want auto ignition of unburnt mixture, because that will be random, then that will create in, knocking. So the ability of a fuel to resistant the knocking, that is called octane number. So you want higher octane number or lower octane number?
Higher octane number.
We want higher octane number, because more the octane number, that means more the ability of the fuel to resist the knocking, right? So sometimes when you go to petrol pump, then you will see some, premium petrol or something like that. Some names will be there, right? One will be a simple normal petrol, and other will be, premium quality and some fancy name for that, petrol. So that petrol is basically is having higher octane number. So now I will ask you one question, that for example, you have a bike and you go to petrol pump, then which fuel you will prefer? The simple petrol, standard petrol, or one with the higher octane number? Which one will we prefer?
Higher octane number petrol.
Okay, but why higher octane number petrol?
Chances of auto ignition is less.
Okay, so you are expecting that there can be some auto ignition, but you know that auto ignition will take place only if the temperature and pressures are sufficiently higher to produce knocking. But your engine is designed to, work in those limits in which there will be no knocking. Okay, so usually your engine will have compression ratio in such a way that knocking does not occur. Okay, so and you also know that efficiency of a petrol engine or a SI engine depends on compression ratio, right?
Yes, sir. Yes, sir.
So if you want higher efficiency means more mileage, right? So higher efficiency means 1 kilogram of fuel or 1 liter of fuel, how much kilometers you are traveling. So it is related to that, right? How much,
Yes.
brake power you are getting, correct? Brake power for
Yes.
uh, brake power for how much fuel you are burning in 1 unit time. So if you want higher mileage, that means that you need to increase the compression ratio, because if you increase the compression ratio, you get the higher efficiency, right? Because the efficiency of auto cycle you have studied, it is related to compression ratio. But if you are not changing the compression ratio, then will the efficiency will be affected?
Yes.
If the compression ratio is same, then uh, efficiency should be same, right? Efficiency of auto cycle,
Yes.
right? So if you're not changing the compression ratio, then you should expect that there will be no change in the efficiency. So what you can do is you can increase the compression ratio. You can modify your motorcycle engine so that the compression ratio is increased. Then you can get the more, compression ratio, and then you can expect more efficiency. But in that case, if the compression ratio is very high, then in that case, the chances of knocking will be higher. So in that case, you should use that premium quality petrol, right? But if you are not disturbing your compression ratio, if you are using your engine as it is without modifying the compression ratio or engine geometry, then you will not get any benefit. Okay, then you will be just wasting your money. Okay, so if you want to use the premium quality petrol, then there should be, engine modification in such a way that you are getting more compression ratio. Otherwise, it is just same. Okay, there can be some difference in the combustion. Maybe good fuel can produce, can provide better combustion. But if we assume that there is no effect on combustion phenomena, the combustion kinetics, only thing that is affected, the only thing that is changing the octane number, then there will be no benefit until unless you are changing the compression ratio. Okay, so if you are going to petrol pump and petrol pump person is saying that please take this petrol, it is having higher octane number, your mileage will be more, then you should not believe him. Okay, because you have not modified your engine. Okay, but if you have modified engine, you have more compression ratio, then definitely you should go for.
Okay, sir.
Okay, okay, anyway, you got the octane number. Okay, one more number is there, that is called cetane number. So cetane number is basically related to how easily one fuel can get auto ignited. Okay, so octane number is related to, is more important for, so octane number, it is more important for petrol engines, and cetane number, petrol like fuels. Okay, and cetane number, it is more important for diesel like fuels. Okay, So what I mean by petrol like fuel is that in the petrol engine you can use various fuel, not only petrol. For example, you can use alcohols, right? You can use ethanol or methanol. Okay. In fact, nowadays at petrol pumps you are not getting the pure gasoline. You are getting the mixture of gasoline and ethanol. You are getting like 15% of gasoline or 20% of gasoline. Okay. So few months or few years, maybe 1 or 2 years ago, you are getting 10% ethanol blend, but now government is, you know, promoting that it has set the target that within coming year, in the coming few years, we should mix around 20% of methanol in the petrol. Okay. So ethanol or methanol, these fuels are alternative fuels and they are having higher octane number. Okay. And diesel have a very low octane number. Okay, so this is one thing, that the fuels which have higher octane number, then they will, most of the time they will have low cetane number. Okay, and when the fuels have high cetane number, then most of the time they will have low octane number. Okay, so as I told you that alcohols, for example ethanol and methanol, they have very high octane number, so they also have very low cetane number. So can you use ethanol and methanol in the diesel engine as it is? Like instead of diesel, if you are injecting ethanol or methanol, will it work? It will not work because the auto ignition temperatures of these fuels is very high. Okay, so they will not auto ignite, and in the diesel engine you are not using any spark plug. The only thing only thing on which you are dependent for combustion is the auto ignition, but the auto ignition temperature of these alcohols is very high, so they will not work. Okay, correct. So diesel, so auto ignition temperature of petrol is more than diesel. Correct. Anyways, I hope a few more things are clear, like cetane number, octane number, right? Have you heard this? If you see any new bike, then on the tank of that bike, you will see that it is written E20 compatible. Have you seen that? So E20 means that you are having 20% of ethanol and rest of the fuel is gasoline. Okay, so basically it means the composition of the blend. Hello. Okay, anyways, I hope you can easily answer this question, that self-ignition temperature of petrol is higher than that of diesel. Okay, so if there is no doubt, then we can move to the next question, question number 3. Okay, so following list A, list and second list provides the operating mode of SI engine and approximate air fuel ratio. Match the correct option. So in list A, there are three modes, operating modes: idling, cruising, and maximum power. Then corresponding to these modes, what should be the air fuel ratio that we have to tell? Okay, so this is also discussed in the lecture. I hope you can easily answer the question. 5% throttle, you remember this? So there is this type of graph, right? Right? So during idling and higher throttle demand, we are running on a rich mixture, right? More fuel, right? And during cruising, mostly we are running at stoichiometric ratio, right? So then cruising, at the time of cruising, during cruising there will be stoichiometric ratio, right? So what is stoichiometric air fuel ratio for petrol engine? We have discussed this question, right? Stoichiometric air fuel ratio for petrol. Okay, but you know how to find the stoichiometric ratio for stoichiometric air fuel ratio for any fuel? Hello? I think I have discussed this thing in some previous session, but if you missed that somehow, then I can explain that again. So do I need to explain that again? How to find the stoichiometric air fuel ratio for a given fuel? Hello?
Yes, sir.
Okay. So quickly, we will see how to find stoichiometric air fuel ratio. Okay. Stoichiometric air fuel ratio. So stoichiometric means chemically correct, right? Chemically correct reaction. So what I mean by chemically correct reaction is that for let us say 1 kilogram of fuel, then for complete combustion of that 1 kilogram of fuel, the minimum amount of air that is required. Okay, so if you are providing the minimum amount of that air to come for the complete combustion of that 1 kilogram of fuel, then the ratio of the amount of air is air fuel ratio or stoichiometric air fuel ratio. Okay, so what I mean is that let us say you have a carbon atom, then for complete combustion of one carbon atom you need two oxygen atoms, right? So you will get CO2, correct? So this is chemically balanced reaction. So for this is chemically balanced reaction, or this is called stoichiometric equation. Okay, so carbon is not okay. So in the fuels, you don't have simple carbon, you have basically some compounds. For example, you have gasoline or diesel. So gasoline or diesel, they are not compounds, they are mixture of certain compounds. For example, in petrol is mixture of many compounds, and the main compound to that is very similar to you know petrol or reference fuel for the petrol, that is called oc- octane. Okay, so C8H18. So this is reference fuel for petrol. So for complete combustion, if you want to write the complete equation for the complete combustion of this fuel, then there will be some air. So what is air? So air is basically there approximately 79% nitrogen, right? And how much oxygen? around 21% oxygen, right, in air, correct? Okay, so let us say you have 21% oxygen and 79% nitrogen, and let us say you have a mole of air, right? So for a balanced equation, on the left hand side there are 8 carbon atoms, so on the right hand also there should be 8 carbon atoms, and carbon will basically convert it to carbon dioxide, right? So 8 CO2, and on the left hand side you have 18 hydrogen, so hydrogen basically will react with oxygen and you will get H2O. So for balancing the hydrogen, the number of hydrogen atoms there are on the left hand side there are 18, on the right hand also there should be 18. Okay, so hydrogen is now balanced, right? Correct. So now you can tell the A, correct? On the left hand side, how much A are there? A into 0.21 into 2. Okay, so these are number of O atoms, oxygen atoms, right? This should be equal to 8 into 2 plus 9 into 1, right? So this should be equal to 17, right? So A you can tell it will be equal to 17 divided by 2 into 0.21, right? So it is around 40, right? So there will be no oxygen left, and only nitrogen will be left, right? So for 1 mole C8H18, you need 40 mole of air, mole of air, right? And you know, mass of 1 mole of C8H18, so 12 into 8 plus 18, correct? And for 14 mole of air will be, right? So air fuel ratio will be 1167.33 divided by 114, right? So for C8H18, the stoichiometric air fuel ratio is 10.24. Let me check. I have done this in previous session, I think. Okay, so it was coming around 15. So we had made some mistake. So I request you to kindly check what mistake we have done. Can you check what mistake we have made? Okay, so this was supposed to be 25, right? 16 plus 9, 25. Here, right? 16 plus 9, it should be 25. Okay. 59.52. Okay. So now you can do this by yourself. So air fuel ratio stoichiometric for petrol, it is 15 point something, right? Okay. So when you are when your engine is at cruising mode, then we are running nearly stoichiometric air fuel ratio. Okay. So during cruising, the stoichiometric the air fuel ratio should be near to stoichiometric. Okay, so near to stoichiometric here in the giving option 16 is to 1. This is closest to stoichiometric number. Okay, so part B should be matched to this one. Okay, and during idling and maximum power, there will be, you know, requirement of rich mixture, right? So during idling, this value is during idling, this value is approximately 10 is to 1. and during maximum power this value is nearly 13:1. Okay, so A should be matched with 1, B should be matched with 2, and C should be matched with 3. So correct option here should be option C. Okay, okay, so this is important. Okay, so this thing is important. First of all, you need to have the chemical composition of the fuel. Then you need to write the chemically balanced reaction. Then you need to calculate that for how that for 1 mole of fuel, how many moles of air is required. Then you need to calculate the molar mass of the fuel. Molar mass means the mass of 1 mole of fuel. Okay. Then corresponding moles of air, how much the mass of those moles of air will be there. Then you just need to take the ratio. Okay. So this is how you find the stoichiometric air fuel ratio. Okay, then if you have actual air fuel ratio, then you can find the equivalence ratio. Okay, so when you have more fuel, that means you are more fuel as compared to stoichiometric fuel, then you have rich mixture. Okay, then phi is more than 1. And when you are running at stoichiometric air fuel ratio, that means phi is equal to 1. And when you are running in the lean regime, then phi is less than 1. Okay, so this is how you find the stoichiometric air fuel ratio. Okay, so this is important that you should practice. Okay, anyways, so now we have question number 4. It says that hydrocarbon fuel propane. So propane means C3H8. So this burns with stoichiometric quantity of air. So stoichiometric means again the chemically correct uh, equation. The molecular weight of fuel is 44. The oxygen molecular weight is 32 and nitrogen molecular weight is 28. Consider the composition of air as 21% O2 and 79% N2, and composition of fuel by mass for carbon and hydrogen to the nearest integer is. So what is asked? Composition of fuel by mass for carbon and hydrogen to the nearest integer at. Okay, so composition is given C3H8, and we are asked to find the composition by mass of carbon and hydrogen. Okay, so additional information is not actually required. Okay, we don't need to write even the balanced equation. We just need to count the number of moles of the number of atoms of carbon and hydrogen. So we have 3 carbon atoms and 8 hydrogen atoms. So for 3 carbon atoms means mass of carbon 3 into 12, right? And mass of H, how much? 8, right? 1 into 8. So 36 and 8. Okay. Okay. So percentage mass of carbon will be equal to 36 divided by 36 plus 8, right? And percentage mass of hydrogen will be 8 divided by 36 plus 8, right? So you can quickly calculate these values. 36 divided by 36 plus 8. So it is around 81%, and hydrogen is around 11%. Okay, these are the values. So which option should be the correct option? The nearest integer. So 81.81. So the nearest integer is 82%, and here 11%. 11 or what? 18. Okay. So the correct option should be option A, right? Okay. Is there any doubt? Okay, so I hope there is no doubt, and we can move to the next question. Okay. Question number 5, using the data given in the previous question. So in previous question, what data was given? Fuel was C3H8 and and the molar mass of air, nitrogen, and the fuel was also given. The ratio of air to fuel on mass flow basis is, it was also given that it is burning with stoichiometric quantity. Okay. Right. So for stoichiometric burning, first of all, what will we do? We have done in previous example of octane. Now we have C3H8. 21% oxygen, 71% nitrogen. Now for complete combustion, three carbon atoms. For three carbon atoms, there should be three molecules of carbon dioxide, and for eight hydrogen atoms, there should be four H2O molecules, right? And nitrogen, and there should be no oxygen left, right? There is this is complete combustion. If there is more oxygen, then there will be some left out oxygen, but for stoichiometric there should be no left out oxygen. Okay, so there should be zero O2. And nitrogen will be the same nitrogen. There will be no reaction of nitrogen. Okay, so again, uh, we have balanced the number of atoms of carbon and hydrogen. Now we need to balance the number of atoms of oxygen. Okay, oxygen atoms. So on the left hand side, how many oxygen atoms are there? There are A into 0.21 into 2, and that should be equal to, on the right hand side, how many oxygen atoms are there? 3 into 2 oxygen atoms in carbon dioxide plus 4 oxygen atoms in H2O, right? So there are 10 oxygen atoms. So A is equal to 10 divided by 2 into 0.21, right? So 10 divided by 2 into 0.21. So it is 23.81, right? So mass of fuel, so 1 mole of C3H8, we need 23.81 mole of air. So for 1 mole of C3H8, what is the molar mass? 44. And for 23.81, there should be 0.21 into 32 plus 0.79 into 28, right? So if you just calculate this value, 23.81 into 0.21 0.21 into 30 into 32 plus 0.79 into 28. So 686.68. Correct? So air fuel ratio at stoichiometric will be what? 686.68 divided by 44 divided by 44. So how much it is? 15.6, right? 15.6. This is the stoichiometric air fuel ratio, right? Where is the correct option? Option D. Okay. Option D, 15.6. This is the stoichiometric air fuel ratio for the stoichiometric combustion of propane, right? I hope this is clear. If there is no doubt, then we can move to the next question. Okay. Question number 6. Shorter mean diameter is defined as. So I think this was not in the lecture. So I need to explain this. So you know that in diesel sprays, what is happening? You are injecting the diesel in the combustion chamber at very, very high pressure, right? And the nozzle hole is very, very small. So spray comes out and there are a lot of droplets, okay? And those droplets are of different size, okay? Some droplets will be smaller, some will be bigger, and they will be moving at some different speeds, okay? When the fuel comes out from the hole, it forms some ligaments, okay? Ligament are like long little long liquid structures, and those ligaments breaks, okay? Then those, after the breakdown of ligament, some bigger droplets will be formed, and when those bigger droplets will move forward, they will experience some resistance due to ambient air, okay? So there will be various forces, like for example, there will be surface tension forces, there will be drag due to air, and if there is some internal motion within the droplet itself, because the droplet will be deformed, okay? So what I mean is, okay, so this is one big droplet, okay? Now this droplet is moving towards right, okay? So what will happen? It will experience some force due to air, right? So there will be air, right? Correct? So what this air will do, this will deform this droplet, okay? So this droplet will be deformed, right, due to the force of air, correct? Due to the pressure of air. Now when this deformation will take place, how this deformation will take place? Initially it was spherical, or it can be of any size, but whenever the deformation takes place, this means there is some internal flows within the droplet, right? So whenever there is deformation, then there will be shear forces due to the viscosity of the liquid, okay? Right? So viscous forces will also work inside the droplet, okay? So there are many processes are going on, right? So one is surface tension force, one is drag, one is shear or viscosity within the droplet, okay? So there are a lot of processes. So sometimes there will be these forces will not be balanced, okay? and this deformation will keep on increasing, and eventually this droplet will be broken into a smaller droplet. Okay, so these bigger droplets will be, break down into smaller droplets. So this breakdown of bigger droplets into smaller droplets, this is called secondary atomization. Okay, and the breakdown of ligament, that was primary breakdown. Okay, okay. So what I mean is that inside the spray there are droplets of different sizes. Okay, so there is a whole distribution of the droplet sizes. Some will be very small, some will be quite bigger, and some will be in between. Okay, so when you have a distribution of different sizes, then what you need a mean diameter. Okay, you need a mean diameter. So how do you calculate the mean? That you already know, right, from mathematics. So how do we calculate the mean diameter? Let us say you have a mean diameter, simply, or arithmetic mean diameter, AMD. So how do we calculate this? If we have, let us say, n droplets, then you just sum the size of all the droplets. Okay, let us say the di is the diameter of ith droplet. Okay, and I will be from 1 to n is the number of droplets divided by n. Okay, so this is your arithmetic diameter. Okay, so this is called AMD. Okay, okay, but in case of engine, what we are interested in the surface area and the volume. Okay, so volume is basically related to the mass. Okay, you know the density, and if you know the volume, then you know the mass. Okay, but we are also interested in the surface area. Okay, the total surface area of the all the droplets. Okay, if you have only one droplet of, let us say, d diameter, then the surface area will be 4 pi d square. But there are a lot of droplets of different surface area. So the total surface area of all the droplet and the total volume of all the droplets, so that is, so ratio of that total volume to the total surface area, that is quite important. Okay, because if you have more surface area, so that means the evaporation will be better. Okay, for more evaporation, what we need more surface area, right? More the surface area, more the evaporation, correct? So we are interested in the ratio of total volume divided by total surface area. Okay, so that ratio is basically what we call Sauter mean diameter. Okay, so for total volume, what will be total volume? Total volume will be 4 pi d cube by 3 divided by sigma 4 pi d square, right? Hello. This would be r square, r cube. Okay, and if you want to write in terms of diameter, then diameter is basically 2r. Okay, so instead of r you can write d by 2. Okay, so eventually if you write in terms of diameter, then this ratio will come out to be, this will be simplified as sigma di cube divided by sigma di square. Okay, so this ratio is called shorter mean diameter. Okay, so this is one of the type of, taking the mean of any quantity. Okay, so if the SMD is smaller, so this means there is more surface area per unit volume, and the more the surface area means more effective the evaporation will be. Okay, and better will be the mixture formation. Okay, so that's why, because this is giving the information about the ratio of surface area and the volume. So this is a very important parameter. However, this SMD itself cannot give you the information about the size distribution. Okay, if you have the SMD value, then you cannot tell that, okay, these many droplets will be up to this size, and these many droplets will be of this size. Okay, so you cannot tell the distribution, but you can tell the overall ratio of total volume and total surface area. Okay, okay, anyways, so this is how we define shorter mean diameter, and there are different type of mean diameters are defined. Okay, so for example, there can be a generalized formula like this: sigma di n plus 1 divided by sigma di to the power n. Okay, and starting from n is equal to 1, you can define various type of means. Okay, in case of shorter mean diameter, n is equal to 2, right, for SMD, and n is equal to 0, 0 or what? Yes, n is equal to 0 for AMD. Okay, so I hope this is clear, and if there is no doubt, then we will move to the next question. Question number 7, it says that which of the following is the characteristic of the spray? So there are four options. Option A, penetration length, cone angle, shorter mean diameter, and all of the above. So I think you can easily answer this question. You know what is the penetration length? Let us say this is your nozzle, and from here the spray comes out. Okay, and this goes up to this point. Okay, so this length is called penetration length. As the name suggests, up to which uh, distance it is penetrated. Okay, so this is called penetration length. And this angle, this angle theta, this is called cone angle. Okay, and SMD or shorter mean diameter we have already explained, right? So all these parameters are the characteristics of a spray. Okay, there are many other parameters as well. For example, different type of means, AMD and some other type of means, and there can be other, characteristics as well. For example, spray area. Okay, so different parameters have different effect on air fuel mixing, and air fuel mixing affect the combustion, right? So the characteristics of spray are very important because they do affect the combustion, and combustion in turn affect the efficiency. Okay, okay, so I hope this is clear. Okay, so these were the questions, and I also wanted to discuss how do we characterize the spray. Okay, for example, you need to find the spray penetration length or cone angle. Then what are the techniques used to find those, parameters? And if you find the, distribution of droplet size, then what are the techniques? Okay. So penetration length and cone angle and spray area, all these, parameters gives the overall information of, whole spray. So those parameters are called macroscopic spray characteristics. And the size distribution and the velocity distribution of droplets, those characteristics are called microscopic characteristics. So for macroscopic characteristics, there are a lot of techniques, and the most important techniques are the shadowgraphy or diffused back illumination techniques. Okay. And for droplet size distribution, uh, there's one technique called phase Doppler interferometry technique. Okay. So if you are interested, then I can discuss these techniques, or you can just read about these techniques yourself. Okay, so these were few questions that I wanted to discuss. If you have any problem that you can discuss, or if you are interested, then we can discuss a little bit about these techniques, how this works. Okay, so this image here, you can see this is a phase Doppler interferometry technique. For velocity and size distribution. Okay, so should I discuss or just I should stop it? Hello.
Discuss, sir.
Okay, so this is not the part of, I think course, but just to give an idea how these techniques work, I can show you some examples maybe. Okay. Okay. Shadowgraphy or DBI. As the name suggests, that it is something related to the shadow. Okay. So let us say here you have your injector and this is your spray. Okay. This is your spray. Okay. And here you have a light source. Okay. This is your light source. Okay. So this spray will block the, light. Okay. So at this side, on the opposite side, there will be shadow. Okay. So if on the opposite side you have a camera, okay, if you have a camera, okay, so this is your camera, let us say, and you take the pictures of this spray, then from the pictures you can find what is the cone angle, what is the penetration length, all those things, right? If you have photo or the picture of anything, you can find, you can measure anything, right? Hello. Okay, so
Okay,
if
sir.
you have, okay, maybe I should say show you some pictures, then it will be, let me check if I have those pictures. I have these pictures in my laptop and I will try to share the screen. Hello, is it visible?
Yes, sir.
Hello. Okay, so what can you say? Some pictures can you say?
No, sir. You are only visible, sir.
Okay. Can you not see any pictures?
No, sir.
Okay, let me try again. Still, now
Not
is it
shown.
visible? Now is it visible?
Picture not visible, sir.
Picture not visible. Okay, let me try again. Now I think it is visible, right?
Yes, sir. Visible. X-ray like film visible, sir.
What visible?
X-ray photo like.
Uh, yes, it is not exactly X-ray, but yes, some sort of X-ray, but not. So here you can see there nozzle, right?
Yes, sir.
So now these pictures are taken at a very high frame per second. So frame per second, you know what is frame per second? So frame per second mean in 1 second how many pictures you are taking. So if you are taking 30 pictures in 1 second, then you know that between picture 1 and picture 2, what is the time difference, right? So these are different pictures, and now you will see that sprays start coming out. Okay, can you see?
Yes, sir. Visible.
Okay, now next picture. Now this is next picture. This is next picture. This is next picture, and this is next picture. And now it has hit the, now it is going beyond our optical axis. Okay, but anyways, for example, up to here you can see the whole spray, right? So spray is developing. So if I check if I have at higher, mm, is it still visible? Hello.
Yes, sir. Yes, sir.
Okay, so now you can see. Okay, so this is at high ambient pressure. So high ambient pressure means the earlier the pictures that I have shown, those were the spray images when the outside pressure was atmospheric pressure. Okay, when you are injecting the spray in atmosphere. Now these pictures are for higher ambient pressure. So these pictures are taken basically inside a chamber, and inside the chamber the pressure was quite high. Okay, so the pressure was 20 bar. Okay, so inside there was a chamber, and inside the chamber there was pressure of 20 bar, and in that chamber you were injecting these spray, and the fuel is ethanol. And so you can see that at 1200 fuel injection pressure, these are the spray. Okay, so you can see, right? You can see that these are the spray. Okay, so the total length up to which this spray is going, that is called spray penetration length. Okay, so spray penetration length means the maximum, the distance of this farthest point of the spray from the nozzle hole. So that is the penetration length. Okay, and cone angle I have already explained, right?
Okay, sir.
Hello. So
Okay, sir. Okay, sir.
so you got how do we record? Okay, and so these were the pictures that you are saying X-ray like picture. So it is quite interesting point. So you know what, how the X-ray works. So X-ray is also some sort of shadowgraphy only. Okay.
Okay, sir.
I don't know if I left the meeting or what.
Okay, sir. Thank you, sir, for your brief explanation.
So okay. So should I stop or should I discuss the PDI as well? Okay. So in X-ray, what happens? Your X-ray basically that can penetrate your skin and your muscles, but that cannot penetrate your bones. Okay. So you have one plate, photographic plate, and that plate is actually white. Okay. That plate is actually white, and here let us say there are some bones. Okay, there are some bones, and X-ray is coming from this side. So X-ray can penetrate your skin. Okay, so when there is no bone, X-ray will come and hit the screen, and at the points where this X-ray will hit, that will become black. Okay, that will become black because this is the property of this film. Okay, but it cannot penetrate the bone. Okay, so when so the shadow of bones will remain there, right? So whenever there is some bone and X-ray is not reaching in that place, so that place will remain white, and whenever there is no bone, so X-ray will hit the screen and that will become black. Okay, so that's why you get the black and bones looks like white. Okay, so that is also the shadow of your bone. Okay, so similar thing is happening here. The We are getting the shadow of the spray. Okay, and this is another technique. This is called phase Doppler interferometry technique. So I will quickly explain how this technique work. Okay, so have you studied the Young's double slit experiment? In Young double slit experiment, there are two coherent, light sources. Okay, so those light sources are having similar frequency, same frequency, and they are coherent. Okay, so when they intersect at some point, then there is some interference. Okay, so if you place the screen at that point, you will see some dark and bright fringes, right? You will see some dark and bright fringes. Okay, so this is zoomed in view of this place. Okay, you will see some dark and bright fringes. Okay, now let us consider that some droplet is coming. Okay, so whenever this droplet will be in the bright fringe, so it will scatter the light in whole room, right? Let us say you have this apparatus in one room, two lasers. Okay, and they are interfering, and there is the formation of dark and bright fringe. So whenever the droplet is in the bright fringe, it will scatter the light in the whole room. Okay, and let us say you have some detector. Okay, so detector is basically recording the intensity of the scattered light. Okay, so when the droplet is in the bright fringe, it will scatter more light, and when it is in the dark dark fringe, then there will be no scatter of light. Okay, so you will get not any scattered light. So at the detector, you will get this type of curve, right? Some more intensity means more scattered light, and no intensity means no scattered light. So this type of graph you will get. Okay, so this is with respect to time. Okay, so the delta time t. So delta time t is basically time between two peaks. So two peaks means the time taken by the droplet to reach from one bright fringe to another bright fringe. Okay, so delta t, and you also know the spacing between two bright fringes, right? How? From your physics. Okay, This is simple, trigonometry, and you can drab that. Okay, so now I'm not going to drab that. You, if you are interested, you can do it by yourself, and if you want, then I can discuss it in some next another sessions. Okay, so this spacing, let us say it is delta D, or let us say some other delta L. Okay, so the spacing delta L, and you know the time from this detector delta T, so you know the velocity. Okay, so this is the basic principle. Okay, so you get the velocity of droplet. Okay, now in this case, these fringes I have made is stationary, but in the actual PDI, these fringes are also traveling, so that we can distinguish uh, the direction of motion. Okay, for example, if the droplet goes from down to bottom, then also you will get the similar, you know this type of graph. If it is going from top to bottom at the same velocity, then also you'll get the same graph. So you cannot distinguish whether it is going from up or down to upward. So for that purpose, to distinguish between the direction, these laser beams are having slight difference in their frequencies, so that this fringe pattern is moving, and there is some Doppler shift. Okay, so then you can also distinguish between the direction. Okay, so this is the main principle, and this is a single photodetector. If you use two photodetectors, okay, then if you plot the graph of light intensities of both photodetector, then you will get the similar graph, but there will be some shift. Okay, there will be some phase shift. Okay, so this phase shift is related to droplet size. So smaller the droplet size, more is the phase shift. Okay, okay, so simultaneously you can measure the velocity as well as the droplet size. Okay, so this fringe pattern will give the one component of velocity, and if you want all three components, so you need three such pairs. Okay, here there is only one pair, and you are getting only one velocity component. For all three velocity components, you need three such pairs. So here the image you can see. So in this one you can see there are green, right? So one pair, and another is to blue. Okay, so another pair, right? And some yellow. Okay, so three pairs are there, so you can get all the three components, and you can observe that they are intersecting at this point. Okay, very small intersection volume. So whatever droplets are passing through that intersection area, so at that intersection area you can get the velocity distribution and the size distribution. Okay, so from that data you can calculate AMD, SMD, and whatever is desired. Okay, so this is how you measure the velocity distribution, size distribution, and the spray angle, the penetration length, or any parameter. Okay, so I hope
Okay, sir.
you learned something new, and I think I should stop here. Okay, so thank you for joining. We will
Thank you,
stop
sir.
here, and we'll meet in the next session. Thank you.
Thank you, sir. Thank you, sir.
Thank you. Bye.
Bye, sir.